Hi friends, today's topic is moment of inertia. So to understand the moment of inertia, let's first understand what do we mean by inertia. So if we have mass m over here for instance, and this mass is moving with some speed, let's say v. So we have got a mass m moving with speed v. So this mass m will have some inertia due to which it will oppose its motion along the straight line. So the inertia is basically opposition to the motion. So in this particular condition, this mass is moving along the straight line. So it has the inertia of straight line motion, and that is caused by the mass. We can say that when a body moves along a straight line, the opposition to its motion will be due to the mass of the body. So here this mass will cause inertia or opposition to the motion. So it means when body moves along the straight line, the factor which is opposing its motion is the mass of the body. Now let's say another example. So we have got door over here, friends. So this door has some mass m, let's say it has mass m, and this is rotating about this particular hinge. Okay, so this is the axis of rotation. So in this particular situation, if you want to rotate this particular door, let's say you are applying some force here, so you apply some force over here in order to rotate this particular door, right? So in this particular situation, you will be experiencing certain amount of resistance to rotate this particular door, right? Now if you just simply put extension over here to the door, you are not increasing the mass, but you are extending its length, let's say, and now this is the axis of rotation. So now here you want to rotate the door about this particular axis of rotation. Okay, so in case 1, when the axis of rotation was here, let's say at AB, and now here we have got the axis of rotation at CD. So the previous case, when the axis of rotation was here, if you apply the force, with less force you will be able to rotate it. So now in this particular case, when you just put an extension and the axis of rotation is shifted to this location, you will find that the force required to rotate this particular door will increase. It means the resistance offered by the body for the rotation will not only depend on the mass, but also it depends on the location of the mass from the axis of rotation, that is R. Okay, so this was the case 1. We talked about linear motion. So in case of linear motion, the mass plays the role of inertia. Okay, inertia stands for opposition to the motion, right? So when body performs linear motion, the mass plays the role of inertia, or we can say the inertia or opposition depends on the mass of the body. But in the second case, if you see, when body performs rotational motion, in that case mass as well as the distance from the axis of rotation plays the role of inertia. So we have got mass and we have got its distance from the axis of rotation, friends. So that is why it is called as moment of inertia, because distance is involved. So whenever distance is involved, we will call as moment of inertia. So like this we can understand the case 2 involves rotational motion, and for rotational motion, friends, you will have moment of inertia, that is the mass of the body which is undergoing rotation, and secondary the location of the mass of the body from the axis of rotation. So please remember, when body performs linear motion, the mass plays the role of opposition, which is called as inertia. When body performs angular motion or rotational motion, the mass of the body as well as its distance, that is R, plays the role of inertia, and which is called as moment of inertia. So now we would like to discuss in detail about moment of inertia. So here it will be also called as mass moment of inertia. Let's say we have got an irregular shape of body. Okay, I have to consider a body of any irregular shape, and so let's say that body is rotating about this particular axis. So axis is going through the body and then it comes out from another end. So this is the axis of rotation. Now we are assuming that the body consists of number of masses. Let's say we have got mass over here. This mass is m1 and it is located at distance r1 from the axis of rotation. So we can also have another mass, let's say somewhere over here, m2, and it is also located at the distance r2 from here, right? Similarly, we can take another mass somewhere here, m3, at distance r3, and likewise we can have number of masses. So let me say We have another mass over here. I am going to call this mass as Mn, and corresponding distance will be Rn. Like this we have infinite number of masses of the body. Now if I simply ask you, what is the moment of inertia caused by m1? So you may say that the moment of inertia will be caused by mass m1 and r1, right? But please remember, the moment of inertia is a scalar quantity. It cannot be negative, it will be always positive. So suppose if I take m1, r1 positive, if I multiply m1 with r1, I get a positive number. So if I multiply by m2 by r2, this also should be positive number. Okay, so to eliminate the confusion with positive and negative, because this you may take positive towards right and towards left you may take negative. So to eliminate the factor of negativity, we will consider squaring of the distance. Okay, so the moment of inertia caused by mass m1 will be taken as m1 times r1 square. Why I have taken r1 square? Why I have not taken only r? Because if I take only r, so that will become a vector quantity, right? So vector means r can be, if it is towards right it is positive, it may be, and if towards left if you take, it will be negative. So this will add the moment of inertia, this will reduce the moment of inertia. But opposition by the body for the rotation will not be reduced. Okay, it will be always positive. That is why I have to consider all distances in terms of square. Okay, so this particular factor m1 times r1 square, so this will indicate the opposition to the rotation of the body. Okay, and this is going to be a scalar quantity because moment of inertia is always positive, it cannot be negative. So moment of inertia is going to be always positive. So that is why moment of inertia will be calculated by multiplication of mass and the square of distance of mass from the axis of rotation. So this I would like to highlight here. The moment of inertia is the product of mass and square of its distance, that is r square, from the axis of rotation. Now this body, if you see here, this body consists of many masses, right? Like m1, m2, m3, and that leads to mn. So if I want to find total moment of inertia of the body, in this particular case it will be total moment of inertia. So the symbol of moment of inertia is I. So it will be the moment of inertia by mass m1, that is m1 r1 square, the moment of inertia by mass m2, m2 r2 square, the moment of inertia by mass m3, m3 r3 square, and so on. There are many masses, and finally we write moment of inertia by mass mn. So this is the expression for moment of inertia of body, which consists of the masses m1, m2, m3 up to mn, and having distances r1, r2, r3 up to rn. Now if you see here, we have considered the masses at various points. So this condition is called as discrete distribution of mass. Okay, so masses are not uniformly distributed, but they are distributed at various points of the body. But what happens if the mass distribution is uniform? Means at every point you have uniform distribution of mass. So we will discuss that particular case also. So I am considering a body here, friends, of any irregular shape, and let's say it is rotating about this axis. This is the axis of rotation, and the distribution of mass is uniform. So if the distribution of mass is uniform, what I will do is I will be taking a very small mass. Let's say I am going to consider a very small mass, which is called as infinite decimally small mass, and I am going to call this mass as dm. dm stands for infinite decimally small mass, and this mass is situated at distance. So this is r. R is a variable distance because this dm is going to move throughout the body, right? It can have any place inside the body. So this r is going to be changing. Okay, so r is a variable quantity. So in this particular case, I want to find moment of inertia for uniform distribution of mass. I'll find out the moment of inertia of this small mass. So it is going to be distance square times mass, that is small mass, right? So this will be the small moment of inertia of this particular mass, right? So I'll say d stands for small, infinite decimally small moment of inertia. So this indicates the small moment of inertia of this particular mass, but not of the body, right? But now if I want to find the moment of inertia of entire body, I will have to integrate this. So if you integrate this like this, friends, you will be getting the total moment of inertia of the body. So let me repeat it again. We will take a small mass which is called an infinitesimally small mass, which is uniformly distributed in the body. So I have taken an arbitrary location over here. So at this location a small mass dm is considered and its distance from the axis of rotation is r, right? So I'll find the moment of inertia of this particular mass, which is mass dm into distance square. But I want to find the moment of inertia of entire body. Okay, so in this particular case I will integrate this, so which will give me the total moment of inertia of the body, which is integration of small moment of inertia, which is integration of r square dm. So like this, friends, we can find out the moment of inertia of a body having uniform distribution of mass. Please understand, the uniform distribution of mass, it means at every point density is same, density is not changing. Okay, but here if you see, which was not uniform distribution, which is called as discrete distribution of mass, here at various points the density is high, or the mass is located at this point, this point, this point, right? So at various points only the masses are available. Okay, the remaining portion there is no mass. Okay, so these are called as discrete distribution of mass. Well, this is called as uniform distribution of mass. So hope it is clear. So in the next lecture we will go ahead and we will try to obtain the expression for moment of inertia of various types of bodies. Okay, thank you very much.